Morning student, I am VN Karnar, PGT Physics from Jawahar Navodaya Vidyalaya, Shega. So dear student, today we are going to discuss about the magnetic field of bar magnet on an axial point. So today's topic is magnetic field of a bar magnet at an axial point. So students, already we have discussed such type of cases in our first chapter, that is electrostatics. In that case, we have find the electrostatic field intensity of the electric field at an axial point. On the similar in the similar way, we'll find here the electric field, magnetic field of a bar magnet, magnetic field of a bar magnet at an axial point. Okay, so now let us draw a diagram for this one. Suppose you are having this bar magnet, having this north pole and this one is south pole. Now let us draw the axial line. So the axial line, this is the axial line on which we will consider here a point P, where we are going to take a unit north pole, and then we will find the magnetic field at this point P. So let this NS, this is the bar magnet of length 2L. So this length is 2L. Length is 2L. So ultimately we can say from the center, this from this O, this distance will be L, and this distance will be L. And we will take a point P on this axial line. This is called an axial line. Okay, so your axial line, on which at this point P we will consider a unit north pole. So the magnetic field is to be determined at point P, which lies on the axis of the magnet at a distance r from the center. So from this point, from the center of the bar magnet, let this point P is located, or we have considered at a distance r. So now we have to imagine, what we have to imagine here? We have to imagine a unit north pole. What is unit north pole placed at this point P? Unit north pole is placed at this point P. Then from Coulombs law of magnetic forces, the force exerted by this north pole, of pole strength Qm, north pole is having pole strength Qm. This is what pole strength. Pole strength Q suffix m on a unit north pole. Then we can write from the Coulombs law of magnetic forces, that is Fn is equal to mu0 upon 4 pi Qm upon r minus L bracket square, and its direction is along n. See here, unit north pole if you are taking here, then this is also north pole, therefore there will be a repulsive force, and that force is in this particular direction. That is nothing but here Fn. And similarly, the force exerted by the south pole now on this unit north pole, since this unit north pole and south pole, there will be attraction, therefore the force will be in this particular direction. This is nothing but your Fs. So Fn and Fs, these are the two forces which are acting at this point P in these two directions, that is opposite direction. See, North Pole repels the North Pole, so in this direction, and the South Pole attracts this unit North Pole in this direction. But since this North Pole is closer to this point P, this North Pole is closer to this point P, therefore this force is greater than this force because South Pole is far away as compared to the North Pole from this for this point P. Therefore, in the magnitude also you can say, or you can say I have shown here the bigger line for this one and here the smaller one, indicating that the magnitude of the forces here. We can say directions are different and magnitude also differs. So the directions are opposite. So Fn and Fs are in opposite direction. And now we have written that according to the Coulombs law, we got this Fn is equal to magnitude of the force due to the North Pole is given by mu 0 upon 4 pi qm upon r minus l bracket square. Similarly, the force exerted by South Pole on unit North Pole is given by Fs is equal to mu 0 upon 4 pi qm upon r plus l bracket square. See here the denominator r plus l, this one is L for the South Pole from the center, and r is the distance of this point P from the center, therefore the total distance will be r plus l. So I have written here the distance square r plus l bracket square. Similarly for this North Pole, I have written r minus l because from the center this North Pole distance is L and the distance from the center to this point P is nothing but your r. Therefore, this distance is given by, you can say, r minus l. So that is written here in this case. So the strength of the magnetic field at point P is the strength of magnetic field at point P is, that is B axial, that means the magnetic field along the axial line is equal to force experienced by unit North Pole at point P. Therefore, as you can see here, these two forces are in opposite direction, and the force due to the North Pole is greater than that of the force due to the South Pole. Therefore, I can write here Fn minus F. So by putting the value, I can write here B axial or magnetic field on the axial line is equal to mu 0 and this qm I will take common upon 4 pi into bracket 1 upon r minus l bracket square minus 1 upon r plus l bracket square. So after solving this, you get mu 0 q suffix m upon 4 pi into 4rl upon r square minus l square bracket square. Solve this bracket. So ultimately you will get this type of equation. But here we can say magnetic dipole moment. Magnetic dipole moment is given by m is equal to qm into twice l. Okay, you are aware of the fact of this magnetic dipole moment, that is given by small m is equal to q suffix m, that is the pole strength, okay, of the North Pole, or as well as the pole strength of the south pole, that is Q suffix M into twice L. So if you put the value in this equation, so B axial or magnetic field on the axial line is equal to, how you can write here, mu 0 upon 4 pi, just split this one, Qm, this 4 and this L. So you can write that one, splitting one you will get this Q into twice L, you can take out from this one. Okay, so remaining terms will be twice Mr upon R square minus L square bracket square. I think you got this one. See, Qm into 4L, I can write here, I want to express in terms of this one. Okay, so this Qm into twice L into 2. So this factor is nothing but M, and this 2 here. Okay, and this R is here multiplied here, R factor is there already. So you can multiply by this by R. So ultimately you will get here R. So this term is 2mr. Okay, so the magnetic field on the axial line is equal to mu 0 upon 4 pi twice mr upon R square minus L square bracket square. So by taking the conditions now, for a short bar magnet, for short bar magnet, L is very less than R. See here, if you take this bar magnet, it is a very small one, and if you take this point P far away, if you take this point P far away, then you can say this length and that R, suppose this one I will take here R, and I can say that this L is very less than R. So that condition I am now going to put here so that I can neglect this this L from this one. So I can write B axial is equal to, what you will get beta? So mu 0 upon 4 pi, mu 0 upon 4 pi into 2mr upon R raised to 4, because I am neglecting this R square now, sorry, L square, because you have taken that L is very less than R. So you'll get this one, cancel this. Finally, you'll get B axial or magnetic field on the axial line is equal to mu 0 upon 4 pi twice M upon R cube. So this is your final expression. This is your final expression for the magnetic field of the bar magnet on the axial line. So in terms of the vector form also, you can write that one, B axial is equal to, if you want to write in the vector form, then you can write here B axial is equal to is twice M upon R. So I think from this, all the steps here, whatever the steps we have involved or we have approached, we got this relation for the magnetic field at an of a bar magnet at an axial point. So the magnetic field at any point on the axial point of the magnetic dipole is in the same direction as that of the magnetic dipole moment. That means you see the direction here. So direction, resultant direction will be in this direction only. Okay. Therefore, we can say whatever the magnetic field you have got, this magnetic field at any point on the axial, on the any point of the magnetic dipole is in the same direction as that of the magnetic dipole moment. Okay. You see here the magnetic dipole moment here. So the direction of the magnetic dipole moment and the magnetic field are in the same direction. Same direction. So this is the final conclusion that we have got from this equation or from this particular derivation of the magnetic field of a bar magnet at an axial point. Now, dear student, we will proceed for the magnetic field of a bar magnet at an equatorial. Magnetic field of a bar magnet at an equatorial. So I hope you have noted down all these things here, and I don't I don't think that you will find any difficulty for understanding this particular derivation. So next one now, the next topic, that second one, magnetic field of a bar magnet at an equatorial line. Equatorial point. Okay, magnetic field of the bar magnet at an equatorial point. So what is by equatorial point? The equatorial point is nothing but if you take this bar magnet, so suppose you are having the south pole and north pole here, then you draw the perpendicular line passing to the center, then you have to take this point. If you take any point on this line, then this line is called as our equatorial line. And if you take the point on this particular line, this is your equatorial line. And if you take any point on this line, then that is called as the equatorial point. And we have to find either you can take to this direction or you can take to this direction. And you have to find the magnetic field. Magnetic field at any point on the equatorial line. So now, dear student, we will proceed for the diagram here. And I think you might have got the idea about this diagram as we have drawn in case of electrostatics also, that electric field intensity at an equatorial point. Okay, so let us draw the diagram here. The bar magnet having south pole and north pole here, then the line joining this one, the center point here O,